we talked about the three states of matter previously, like back in chapter 1. But now I want to talk about the states of matter again, talking about their energy. So this slide has a whole lot of words, and I'm not going to read through it all. But basically, I just want to compare solids, liquids, and gases in terms of their energy. So gases are going to have the most energy. The particles are going to be far apart. And that's because there's going to be no attractive forces between them, so they're able to move around. Solids are on the other end of the spectrum. They're going to be held really close together by stronger attractive forces between the particles. So because of that, there's little movement of those particles, so they're not going to have as much energy. Going to have much lower energy, and those particles are going to be kind of stuck still. And then liquids are kind of in between. They have properties kind of intermediate of solids and gases. They have some attractive forces, but not as much as solids. They do have some energy, and they're a little bit further apart, but not as much as gases. All right, so just in general, whenever you're thinking about energy of molecules, think about the differences between solids, liquids, and gases in terms of those particles and how close they are to each other, and then the energy that might hold them together. So that being said, what I want to do now is go in to talk about these attractive forces that hold different chemicals together. So our intermolecular forces are going to be attractive forces that exist between separate molecules, and there are three different ones we're going to talk about. So London dispersion forces, dipole-dipole interactions, and hydrogen bonding. So these are from weakest to strongest, and then the strength of these forces are important to determine physical properties of compounds. So one thing we're going to look at this semester with a lot of different chemicals and molecules is look at whether they have a high boiling point or a low boiling point, or being able to look at two different chemicals and predict which one has a higher or lower boiling point or melting point. And basically the idea here is the weaker the forces between the molecules, the lower the melting point or boiling point would be. And if you imagine it this way, if you think of a solid and it doesn't have a whole lot of attractive forces, so it has weak attractive forces between those atoms within the solid, it doesn't take a whole lot of energy to overcome those forces and get those molecules further apart, which is going to turn them into a liquid. Or if they're in a liquid, it's not going to take a whole lot of energy to overcome those forces to turn it into a gas. Right? So the weaker the forces, the easier it is to move from one state to another. The stronger the forces, the more energy it takes, the more heat it takes, which means it's going to have a higher melting point or boiling point. All right, so let's go through and look at these different interactions, the London forces, the dipole-dipole interactions, and the hydrogen bonding. So London forces are going to be the first set of these intermolecular forces we talk about. These are the weakest of the three forces we're about to talk about. They're also probably the most difficult to understand. So these are going to be really weak interactions that are also very temporary interactions. And if you look at the first bullet point here, it says, the change in electron density creates a temporary dipole. So remember, a dipole is when you had, like we looked at it in chapter 3, there was unequal sharing of electrons between two elements. We said the one that's more electronegative kind of steals its more than its fair share of electrons. Well, what happens in London forces, and again, these actually occur in all covalent compounds. So anytime you have a compound where you have the sharing of electrons like this, you're going to have these London forces. So what happens in London forces is you have two molecules like that. So these are both CH4 molecules. So you have carbon in the middle and then hydrogen surrounding it. And if you look at over here, this says partial negative on this side, and then it has partial positive over here. This one has partial negative. This one has a whole bunch of partial positives. So those partial negatives and partial positives come up. If you think about this, carbon has a total of 6 electrons in it, and hydrogens all have 1 electron each. So there's a total of 10 electrons in a CH4 molecule, if you're just to add up all the electrons from all of the elements. So imagine you have a CH4 molecule, and I'm going to draw it like this circle. And you have the nucleus, right? The nucleus is where you have all of your positive charge, right? That's where you have the neutrons and the protons. But you have 10 electrons floating around. Those electrons can be imagine you take a picture, and at one point you take a picture, and I'm going to have all of the electrons be negative charges, these minus signs. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and I'll put another one over there. So you can see at this particular point, like if I take a snapshot picture, I have more electrons on the left than I do on the right. So that means that this side of the molecule over here is going to have a partial negative charge, and this side over here is going to be partially positive. All right, so let me do another one down here in blue. All right, so one in blue, there's my kind of circle. So in this case, a couple seconds later, let's say you take a picture, right, with your iPhone or whatever, and the electrons are scattered like that. Well, in this particular case, you're going to have a partial negative charge over there on the right because the electrons are more congregated on the right. And on the other side, it's going to be partially positive. So that's exactly opposite of what we had in our first example where the electrons were on the left, which means that's going to be a partial negative, and that side's going to be a partial positive. So it's the exact same chemical. It's still CH4. It's just saying at random different times, it can look different ways. Now, going back to the example from the picture in the book, if you have this one over here on the left that has the partial negative on the left side and a partial positive on the right, and it happens to get really close to another molecule that has a partial negative over here and a partial positive over on the right, what's going to happen is the partial negative that you see here in the middle and the partial positive, those are going to have an attractive force to each other. Opposites attract. So the positive is going to be attracted to that negative here. Right? So these two are going to interact with each other and help hold it together. Now, it's a temporary force because those electrons are always going to be moving. So, like I said, a half a second later, a few milliseconds later, those electrons could move, so they're no longer going to have those attractive forces. So, these are going to be very weak interactions between temporary dipoles, and that's what a London force is. All covalent compounds have them, and the larger the molecule, the stronger those forces will be in total. And the reason for that is, if you had, in the example I just looked at, I had 10 total electrons there. Well, imagine if you had a molecule that had 100 electrons in it. If you were to get 90 of those electrons on one side and only 10 on the other, you could have a much larger in magnitude partial negative charge on one part of the molecule. So the larger the molecule, the stronger those forces can be because you can have a larger negative and positive charge interacting with each other between two compounds. Okay, so those are London forces. Again, the important thing there, they're weak and they're temporary. All right, so now let's go to dipole-dipole interactions. So again, with these intermolecular forces, we're looking at interactions between two different molecules. So here's formaldehyde, and you have formaldehyde number 1, you have formaldehyde number 2, and you have formaldehyde number 3. Well, in a formaldehyde, you have a carbon and an oxygen, and we have already talked about that you need to know that a carbon-oxygen bond is polar, and that the oxygen is going to be partially negative and the carbon is going to be partially positive. Right? The oxygen takes more of the electrons. So because of that, this is going to be a polar molecule. It's going to have a permanent dipole. Right? So unlike the one we just looked at, where the strongest force it had was a temporary dipole, this one's going to have a permanent one. So this permanent dipole means that every formaldehyde molecule we look at is going to have a partial positive there and a partial negative there. So what happens here with these formaldehyde molecules is whenever they line up, the partial negative is going to be close to the partial positive on the adjacent molecule. So it's going to be an interaction or a force that holds these two things together. And that we call a dipole-dipole interaction. So again, this occurs between polar molecules. Now, I should point out, even though these molecules have dipole-dipole interactions, they also have London forces. London forces are present in all covalent molecules. So London forces are still present here, but they're just much weaker than these dipole-dipole interactions, which are permanent dipoles. All right, so I guess technically you could say formaldehyde has both dipole-dipole interactions and London forces. It's just the dipole-dipole interactions are much stronger than the London forces. And that brings us to the last of the intermolecular forces, which is hydrogen bonding. So hydrogen bonding occurs with hydrogens. And even though it says bonding, it's really not a bond. It's still more of a force. It's kind of a misnomer. It's given that because it's a really strong force, though. So this is when a hydrogen, but not just any hydrogen. It has to be a hydrogen that's attached to an O, an N, or an F. So it's a hydrogen attached to an O, N, or F is going to be attracted to an O, N, or F in another molecule. So, for instance, in water, here is your hydrogen right there. So that's a hydrogen that's attached to an O, right? Hydrogen attached to an O. That hydrogen that's attached to the O is going to have a hydrogen bond with another O, N, or F, in this case another O, right, from a neighboring water molecule. So that's going to be a hydrogen bond. So again, these hydrogen bonds are going to be the strongest of the forces. If you really thought about what's happening in water, you would say it has hydrogen bonds. It would also have dipole-dipole interactions because this is going to be a polar molecule. And it's going to have London forces. But again, usually like on a test or something, I'll ask you which is the strongest force that a particular molecule has. But you should be aware that all of them do exist between them. Again, it's the London forces from the temporary dipoles are going to be negligible compared to the strength that's given by these hydrogen bond forces that hold the two water molecules or whatever molecules together. Hydrogen bonding is actually really important in a lot of biochemical processes. So here's an example with DNA. We'll talk about this in actually the very last chapter of the semester. But you probably have heard of DNA and seen the structure before, but these are your bases. So DNA is going to be this double helical structure. And what holds the two strands of the helix together here, these little lines in between the two strands, are used to depict these hydrogen bonds that hold it together. So hydrogen bonding is important in holding together our DNA and giving it the shape and the structure that it does. All right, so here's a summary table of the forces. Again, London dispersion forces are going to be the weakest, dipole-dipole are going to be in the middle, and then hydrogen bonding are going to be the strongest ones. And again, remember that for hydrogen bonding, it's only hydrogens that are bound to O, N, or F. All right, so which forces do each of the following exhibit? If we were to look at NH3 and we could draw it out, we would say it's NH3 like this. It would have a lone pair of electrons. We have hydrogens that are bound to nitrogens. So that means this one would have hydrogen bonding. Hydrogen bonds. It would also have it's also polar molecules, so it would have dipole-dipole interaction, and it would also have London forces. The strongest of them would be the hydrogen bonds. Water, we just talked about on the previous slide, and I went through how it would have all of them as well. Hydrogen bonds, dipole-dipole, and London forces. For HCl, I would actually have to tell you since it's not one you would have to memorize, but HCl is polar. So the bond between hydrogen and chlorine is polar, with chlorine being partially negative, the hydrogen would be partially positive. So if it's polar, that means it's going to have dipole interactions and London forces. Again, the London forces would be negligible compared to the dipole forces, though. And then the last one, C2H6, if you're wondering, it would look something like this. That's our C's in the middle. H is on the end. You really don't need to draw this one out, though, because if you only have carbons and hydrogens and you don't see any other atoms in there, it's always going to be nonpolar. right? Because we know carbon-carbon bonds are nonpolar. Anything bound to itself is nonpolar. And then carbon-hydrogen is another one I told you had to memorize that are always going to be nonpolar. So because of this, it's going to be nonpolar, which means that the only forces it would have would be London forces. And if we went through and looked at these, and we tried to rank them in terms of which one would have the highest boiling point, well, it would either be NH3 or water because they have hydrogen bonds, right? The stronger the forces, the higher the boiling point or the melting point would be. After water and NH3, the next highest one would be HCl, and then the lowest one would be C2H6, which is ethane. Interestingly, these are all liquids at room temperature, and then ethane is actually a gas at room temperature. Weaker forces means the heat at room temperature is able to get it into the gas phase. So just to reiterate what we've been talking about in terms of relating the strength of the forces with the boiling point and melting point. So you can see down here, the weaker the forces, so compounds with only London forces are going to have lower boiling points and melting points, and then compounds that can hydrogen bound are going to be the higher ones. So this is the same thing I've said before, just looking at it in a graphic form. And then just a reminder, boiling point is going to be the temperature at which a liquid is converted to a gas. And it's also the temperature at which a gas can be converted to a liquid if you're cooling things off. Right, so it's basically that phase change between liquid and gas going in either direction. Similarly, the melting point is when you go from a solid to a liquid, or you could go from a liquid to a solid. So, right, the melting point or the freezing point is going to be the same thing. Okay, so taking an example and looking at this, here is methane, CH4, that has only London forces, and comparing that with water that has hydrogen bonding. Right, so we know that hydrogen bonds are a stronger force, and you can see the difference in the boiling point, BP, versus the melting point, MP, comparing methane to water. So water has a much higher boiling point, and it has a much higher melting point than methane because of those stronger forces. You should be able to look at a boiling point and a melting point for something and say what temperature or what state of matter it is at any given temperature. So for instance, think of it as a graph like this. You have boiling point, and then you have melting point, right? And it goes like this. Right, so you kind of have increasing temperature as you go to the right. So on the far left, something is going to be a solid. And then after you go past its melting point, then it's going to be a liquid. Then after you go past its boiling point, it's going to be a gas. So in the case of water, if the melting point is 0 and the boiling point is 100, if I said what state of matter is water going to be at 120 degrees, you would say, well, there's 100. It's going to be over here. It's going to be in a gas. If it's between 0 and 100, it's going to be a liquid. If it's less than 0, it's going to be a solid. Right? For methane, right, I can put those same numbers down here for methane, except I'll do it in blue. Negative 183 is the melting point. Negative 162 is the boiling point. So I said, what is methane going to be at negative 150 degrees Celsius? Well, that is warmer than negative 162. So even at negative 150 degrees Celsius, methane would still be a gas. All right, and then only between negative 183 and negative 162 is it going to be a liquid. And anything colder than negative 183, it would be a solid. All right, so you should be able to look at boiling points and melting points and determine state of matter from that. So if we were comparing propane and butane, so these are the two structures you're looking at down here. They both are nonpolar. So they both only have London dispersion forces. However, because butane is larger, notice it has 4 carbons and 10 hydrogens as opposed to 3 carbons and 8 hydrogens in propane. Because it's a larger molecule, it's going to have stronger attractive forces. Remember, I kind of said that before. The London forces are still weak, but the larger the molecule, the more overall electrons there are going to be, and the stronger those temporary dipoles will be. So butane is going to have higher forces than propane because it's a larger molecule. All right, so let's take a look at this last slide here in this section and determine which has stronger intermolecular forces between in any given pair. So carbon dioxide and water. Well, CO2, if you remember, CO2 was an example we gave that looked like this, and we said it was nonpolar because the two polar bonds themselves canceled each other out. So since CO2 is nonpolar and water can actually, not only is it polar, but it can hydrogen bond, water is going to have much stronger intermolecular forces. So the reason here is because of hydrogen bonding. Okay, so for the next one, CO2 or HBr. So again, CO2 is going to be nonpolar. HBr, I would have to tell you, or maybe better yet, I would probably give you maybe a different type of polar molecule, but this is going to be polar, with bromine being partial negative, hydrogen being partial positive. So because of that, it's going to be HBr, and in its case, it's because it has a dipole interaction, right, which is going to be stronger than CO2, right, which only has London forces. All right, and now in the last set, CH4, which is methane, or C2H6, which is ethane, they're both nonpolar, so they're both going to be nonpolar. So that means they're both only going to have London forces. So how do you know which one is going to be stronger? It's going to be the one that's larger, right? So because they both have London forces, you look for the larger molecule. In this case, it's going to be C2H6.